Okay, we've covered the Bohr model of the atom. And the Bohr model is sort of this familiar idea where there's a dense positive nucleus around which the electrons orbit around as sort of these tiny particles. This model fails in many instances, and this has caused people to develop what's called the quantum mechanical model of the atom. And the quantum mechanical model of the atom was sort of kicked into existence by two ideas we'll discuss. One is Heisenberg uncertainty, and the other one is de Broglie waves. Heisenberg uncertainty is the idea that you can't simultaneously know where a particle is and how fast it's moving. De Broglie waves are this idea that particles can sometimes be described as waves. So just like a photon is a particle of light, so to speak, and light can sometimes be described as a wave and sometimes a particle, it turns out that particles such as the electron or the proton can also sometimes be described as a particle or a wave. And so these two ideas, that particles like an electron can be described as a wave in some instances, and of course if you can't know exactly where a particle is, this sort of lends to the idea that the particle is smeared out in space, or in that instance it's wave-like. The quantum mechanical model of the atom looks at electrons as waves. Now, in the Bohr model of the atom, the energy of an electron can be described with one quantum number, and that quantum number is n. You might remember that the energy of the nth level in the Bohr model could be calculated as the minus energy of the hydrogen atom that we called negative 2.18 times 10 to the negative 18 joules divided by n squared. In the quantum mechanical model, where we look at the electron as a wave, there are four quantum numbers that are required to describe how an electron behaves. And those four quantum numbers are n, l, m sub l, and m sub s. Now we'll describe each of these in turn. Now you should recognize that the quantum model, which uses electrons as a wave, the electrons are described in what are called probability waves. In other words, these are regions of space that describe the probability of finding an electron. These probability waves are also called orbitals. And again, there are four quantum numbers that are going to be required to describe an electron in a particular orbital. Let's look at these four quantum numbers in turn. We'll first look at n, which we sort of saw this idea before in the Bohr model. This is called the principal quantum number, and you can think of this as the shell number. The second quantum number is L, and this is also known as the angular momentum quantum number. And the way I like to think about the angular momentum quantum number, it's the shape of the probability orbital, or the probability wave. So we can also call this the shape of the orbital. And again, the orbital is this region of space in which the electron is likely to exist. M sub L, this is the magnetic quantum number, and this describes how the orbital is oriented in space. So this describes the spatial orientation. And then finally we have m sub s, and this describes the spin. And this, although this is not perfect, you can think about this particular quantum number sort of describing how the electron spins on its axis. So if we imagine sort of like a spherical electron with a pole this way and a pole that way, this is sort of rotating around its axis, kind of like the Earth rotates on its axis. This is not exactly what's happening, but it just gives you a little physical picture of what we might mean when we describe the spin. So if you think of the four S's, N is the shell, L is the shape of the orbital, M sub L is the spatial orientation of the orbital, and then M sub S is the spin. And so we get the four S's: shell, shape, spatial orientation, and spin of the four quantum numbers.